Okay, so in this video I want to do something a little bit different to what we have been doing in the previous vector videos, and I want to introduce you to a very powerful idea. And if you have done any linear algebra before, you might remember that if you're given a system of equations like this, and then let's say minus 2x plus 3y equals minus 1, then you can use matrices basically just to solve this system, and you know that is basically it. You find a value for x and a value for y that basically satisfies both equations at the same time. Obviously that's not always true because a system does not necessarily have a unique solution, but when you do introductory linear algebra, people tend to skip a few things that I think are really important to point out. So where does this idea of solving systems of equations, or essentially just systems of linear equations, come from? Well, in this case, we have two systems. Well, we have a system, but we have two equations and two unknowns. Now, what you might recognize is that these two equations here are actually equations of a straight line on the Cartesian plane. So we have for x, y axis here, this will be a line, this will be another. So just for the sake of generality, I'm just going to draw two straight lines going like that. And essentially, the x and y solutions to this system of equations will be the point of intersection of those two straight lines. So basically, this will be something like x naught, and then this will be y naught. So there's a single point here, P, and that value of x, that value of y, those are the solutions to your system of equations. Not this one in particular, but any system of equations. Now what happens is you will always have a unique solution for a system of two equations with two unknowns, because there will always be a point of intersection between two lines, as long as they're not parallel. So what happens when two lines are parallel to each other? So you might have something like this. So this line is parallel to that one. Well, logic will tell you that these lines are never actually going to cross. So for a system like this, you're actually never going to have a unique solution. In fact, you have no solution because there's not a single point on this plane that would actually satisfy both lines at the same time. And even though they might have the same gradient, so for example, this line might be something like x plus 5, and then this line will have the same gradient, so it would also be a gradient of 1, but it will have a different y-intercept, so it might be something like this. And in general, there is no unique solution because you cannot really find a value that solves both at the same time. So this is what we mean by having no solution. This is what we mean by having a unique solution to a system of equations. Now let me extend this further and say that we have a third equation. Now we have two unknowns. And let's say this is equals to 3. Okay, so things now get a little bit more complicated because now we have three lines. And there are three possibilities here. So assume that we have a general system of equations. Either all lines cross over at the same point, so if all lines intersect at a single point, then there is a unique solution. And in fact, there will be just two unique values of x and y that solve all three equations at the same time. Or you can have a situation like this in which two of the lines cross over at some point P1, but then the third line comes in and it actually crosses over with the other two lines at two different points, let's say P2 and P3. So now what's happening is you're going to have three sets of x and y values, but each of those sets is only going to solve two of the three equations at the same time. So this is what we will call a system that is not solvable, because you cannot really solve all three equations at the same time. So there is no unique solution. And of course, you can also have the case in which all three lines are parallel to each other, but we both know that that's not a very interesting thing because we can tell right away there's no solution to that system. Okay, so that so far so good, and I think this is a very intuitive kind of thing. So you might think, well, that seems like a very reasonable kind of explanation of what linear algebra is and where it comes from. But when we deal with higher order systems, so let's say we have something like ax 3x plus say 6y minus 7z equals to 0, and then 4x minus y plus 5z equals to 2. Now, what do these equations represent? We have three variables. They're all linear equations. These represent equations of planes in 3 dimensions. So if I were to draw a set of axes here, x, y, and z, then what's going to happen is we're going to have 2 planes. We might have a plane that is going in like this. So I'm going to draw it in blue. And now we're going to have another plane that might actually be going something like this. And we need to remember that both planes are actually going off to infinity. Now the interesting thing is, what happens when you have a unique value of x, y, and z for both of them? Well, you're not actually going to get a single point, because remember, when 2 planes intersect each other, the point of intersection is no longer a point, but rather a straight line that extends to infinity. So in the case of 2 planes that intersect each other, you're going to have an infinite set of solutions, because every single point that lies on that line where the 2 planes intersect is going to be a valid solution to this system of equations. So this is why, even though we have more unknowns than we have equations, this system still has a solution. But it's not a unique solution as you might expect. It's actually an infinite set of solutions. So basically, any point that lies on that line is going to be a solution to the system. So that's a really powerful concept. Now let's say we introduce a third plane, something like this. Minus 0y plus z equals to 5. I'm just playing around with these ones here, by the way. Don't take these planes too seriously. But an interesting thing happens here now. If we have a third plane coming in, and I think it will get a little bit messy now, but you can imagine that there is actually going to be a single point. There will be a single point at which all 3 planes are going to intersect. Now what is going to happen in that case, as you might imagine, if all 3 planes intersect at a single point, then that single point is going to be a unique solution to the system, because it is going to be a point that has x, y, and z, and those specific values of x, y, and z are going to solve all 3 equations at the same time. So that is what we mean by having a unique solution to a higher order, or basically a higher system of equations. In essence, this is all linear algebra is. Linear algebra and matrices used for solving systems of linear equations are all based on this concept that you have planes that are intersecting each other, and basically how they intersect each other is going to determine the nature of the solutions that you get for the system. Now you can imagine that if you added a 4th plane, so I'm not really going to give you an equation, but I'm going to give you a general idea of what's happening. You could get a 4th plane, but that 4th plane does not necessarily need to intersect any of the other 3 simultaneously. It could only actually be intersecting them. Or in fact, because these planes extend to infinity, it could intersect the other 2 or 3 planes, but at different lines. So in that case, you wouldn't really get any solutions. You would just get a bunch of solutions that are only valid for a certain pair of planes or so on. And the really interesting thing about this is that if you really think about it, you can extend this to any number of dimensions. Of course, in that case, that wouldn't actually be geometrically meaningful. But in essence, when you're dealing with a system of n equations and n unknowns, let's say n equations, n unknowns, something like that, what you're essentially doing is you're having a bunch of axes here. So I'm just going to draw an interpretation. And then you can imagine that you're going to have something called hyperplane. So a hyperplane is essentially a plane that exists in higher dimensions. So, for example, a plane that exists in 4 dimensions will actually have 4 variables. It will have ax plus by plus cz plus d w equals to some other constant e. So this is the equation for a plane in 4 dimensions. So basically you can imagine that there will be lines, and basically if two hyperplanes in 4 dimensions intersect each other, they actually don't intersect each other at a line, but rather they intersect each other at a whole plane in 3 dimensions. So things get a little bit more complicated to visualize, of course, but you can imagine that this concept keeps expanding into infinite number of dimensions. So we have developed an entire field of mathematics simply by taking into account the properties of straight lines and the properties of planes. So I think that's a really powerful concept, and it's just amazing because linear algebra really appears everywhere you look. It's one of the main building blocks of mathematics, and it is all built around this idea that you have intersecting lines and planes. So this is just a video that I wanted to make just to show you where this comes from, how linear algebra was developed, and just to give you some intuition as to what you're actually doing when you're solving a system of equations, because at least I find it very interesting.